Today we're going to finish off 9.1 and we're going to look at applications. So we're going to look at working with vectors, but this time we're going to use questions involving travel of some sort. One of the ways you can use vectors is to kind of model something moving in two-dimensional space. So in question 24, we have a jet engine that's flying in the direction of north 50 degrees east. Now, if you're not used to that way of direction, basically, there's north, my pen, and you go 50 degrees east. And the question is just simply asking us to find what the north and the east components are. So almost all of this involves you having to figure out what they mean by that direction. And what do they mean by a north and an east component? Because once you figure out what they mean, it's actually a question you know how to do. So first things first, that's 50 degrees. But the angle that we use when we measure the angle of any vector, and this vector V is the aircraft flying at 400 miles an hour, the angle that you use is always the one it makes with the x-axis. So you're comfortable with the real angle, the one that we need is the 40 degrees, not the 50 that they told us, right? So 50 degrees east of north is that, but the one we want is this piece here, which is 40. Now, when they talk about the east component, can you think of the x-axis as east, right? And the y-axis as north. So the east component is just saying, what is the x component of this vector? And the north one is what's the y component of the vector. And we know the formula for that. The x component is the magnitude of the vector times the cosine of the angle. So in our case, the magnitude is the speed. So that's 400 multiplied by the cosine of 40 degrees. And this one is 400 times the sine of 40 degrees. And then you just got your calculator, and that guy is going to be 400 times the cosine of 40 degrees. So that's about 306.4. And the other one, miles per hour. So it's basically flying at about 300 and change miles per hour east every hour. And at the same time, this one here, which is 400 times the sine of 40 degrees, it's also flying north about 257.1 miles per hour. And for every hour, you're going to go 300 and change this way and another 250 that way, which is basically that direction forever. And that's the end of 24. And let's look at 25 then. This is the answer to 25. Let me read out what this looks like as a story. A river flows due south at 3 miles an hour. A swimmer is attempting to cross a river by swimming due east at 5 miles an hour. Find the true velocity of the swimmer as a vector. Now that is not actually that difficult. Does anyone want to have a shot at it? Because you don't need to do really any calculations worth talking about. I want a vector that represents that true velocity of this one.
Do you just add the vectors together or no?
It could be. Depends what you mean when you say add the vectors. In this case here, essentially, don't you go 5 along and 3 down? 5 along and 3 down.
Do you use the Pythagorean theorem?
Not even that. Can you see what I've just done? 5 along and 3 down. That was the answer. I mean, it was almost, you didn't do anything, right? Now, Pythagorean theorem would be correct if they had said, what's the true speed? Because we tend to use these words as if they meant the same, but if you're being really specific, they are different. A velocity is a vector, right? It's a movement in space. A speed is a scalar, a single number. Now, if I wanted to know what the true speed that this person as they swam, it wouldn't be 5 miles an hour, nor would it be 3 miles an hour, right? Wouldn't it be the length of this vector? So true speed is always going to be the length of the velocity vector. And so that's when you would have done your Pythagoras thing, right? That's when that would have made sense. So that's, I think, square root 34, and that would be miles per hour. So anytime they use the word velocity, your answer is going to be a vector. Anytime they say speed, your answer is going to be a number, right? Got those two in your mind. Why did I put -3 here?
Because it's down 3, not up 3.
Yeah, it's down a way. Pretty much that's all it is. Down a way. So here's another one about a little bit more involved in the first two. A pilot heads due east with a speed of 400 miles an hour. So I'm going to draw that. Okay, that's the pilot, right, the jet. And it's going to go 400 miles an hour. 400 miles an hour means that the length of that vector is 400. Okay, and it's flying obviously east because that's where it's pointing. Now the wind is blowing north at 30 miles an hour. So let's have the wind going this way. And the wind is blowing at 30 miles an hour. And they ask us these 5 questions. Now, if a jet tries to fly east and the wind blows it, won't the true path of the jet be this one? Does that make sense? It would get blown a little bit off course, essentially. So, question A, express the velocity of the wind as a vector. Now, the wind is going straight north at 30 miles an hour. So the wind is a vector. Let's call it W for short. Straight up 30. What does that look like as 2 components in a vector?
0, 30.
There you go. The question B wants you to do the same with the jet. And I'll just call that J. And the jet is going east at 400. So that would be 400, 0. Are you comfortable with that? Now, suppose the jet was going to go west for 400 instead of east, right? Suppose it flew west at 400. What would be the minor change to this?
It'll be negative.
Right. And suppose the wind was blowing south, wouldn't you make this negative, right? So north is positive, south is negative, east is positive, west is negative. And that's part B done. Now, it then says, do the true velocity, right? And let's call that guy T. Well, the true one, the red one here, isn't it basically these 2 guys added together, which might have been, now I'm thinking about it, is that what you were thinking about, Cassandra, when you say add the vectors together?
Yeah.
Yep, that's exactly what you should have done. Are we comfortable with the wind, the jet, and now the true velocity? Right. So that red line would be 400 along and 30 up, right, if you wanted to draw it. So this bit is going to be what Lena was talking about. They want us to find the true speed of the jet. And that you get by using Pythagoras. And I believe they want these answers as decimals. And what do they want the answers to be? To the nearest whole number. Okay, that'll make my life a lot easier. So there we go. Square root of 400 squared plus another 30 squared to the nearest whole number. That's about 401 miles per hour. If there was no wind at all, that jet would do 400 miles an hour straight east, right? If it was in a still air, off it goes. Why is its true speed a little bit bigger?
Because it's not going at a horizontal plane, it's going more of an angled.
Right? Isn't the wind giving it an extra little push? Not a lot. 401 compared to 400, right? It's almost negligible, right? But it is giving you a little push. If you ever fly to Europe, and I do it, or used to do it before COVID kicked in quite regularly. Do you know when I fly from Seattle to Glasgow, and then I come back home from Glasgow to Seattle, same jet, everything else is pretty much the same. Do you know it takes me an hour, well, not even an hour, 45 minutes. It's 45 minutes quicker coming back than it is going. Is that the right direction? No, going than it is coming back. And the reason for that is that there's an upper wind called the jet stream that you might have heard of. And the jet stream, when you're going to Europe, gives you an extra little shove. So your aircraft goes a little bit faster, so you get home, you get to Scotland quicker. And when you're coming back, it's a headwind that's pushing a little bit against you, and it slows you down. So that's pretty much known by lots of people, who deal with this kind of thing. So that's the true speed. There's one last piece. Find the direction of the jet. So I'm going to find that angle. Now we know how to find that angle. Isn't it the angle a vector makes given by that formula, right? Remember? And in this case, the numbers that they're talking about are these guys here. So it's the inverse tan of 30 over 400. And so I'm going to go in here, and they want this answer to 1 decimal place. So inverse tan of 30 divided by 400, and I get about 4.3. Yeah, 4.3 degrees. And that is theta. And if I put that into Weber sign, it's wrong, because they want the answer to be written that funny way. So if I tell you that this guy is 4.3 degrees, the angle they want to know is north so many degrees east. So the right answer is actually, well, take that away from 90, what do you get? 95.7, not 85.7 degrees. See that little hiccup at the end that might catch you? The formula that we get always tells you the angle with the x-axis, and that is perfectly fine, but sometimes they don't, sometimes they won't. This angle up here is the one they're looking for. 27, pretty much the same, so I won't do any like that guy. And then we finish with one last question, which I'm sure I've written down. I'm just trying to find my piece of paper. What up? Excuse me for a minute. What are you hiding? Oh, that's my calc stuff. Okay, we'll do it again. I'll show you the question, and it's not to do with journeys. It's a kind of question you might get in a physics class when you're trying to find the total force acting on an object. So here we go. There we are. So yeah, this is going to feel like a physics class, but even if you don't do physics, we can still get the answer. I don't know if I'm in the right place here. I could be. Are you looking at question 28, guys?
Yes.
Okay, we're in the right place after all. We are going to be looking at this guy at the origin. I want you to think of that's where, I don't know, let's do a tugboat story. There's a tugboat right there at the origin, right? Or a big ship at the origin. And there's a tugboat pulling it this way with a force, let's say 15 tons and the angle is 60. And one over here at 12 and one down here at 9. Now, if you combine these three forces together, you'll probably get a single force pointing roughly in this direction here. Does that seem reasonable? And our job is to find what that is. It's called the resultant force. And that's something that you would want to do in a situation where there's lots of forces acting on a body, right? What's the total force, essentially? And we're going to do that by using vectors. And if you give me a few seconds, I'll try and set it up for us. And I'm just going to do one at a time. So the first force is going to be called F1. Has a magnitude of 15, so you write 15 there. Change my pen, red one's down on me. And the angle that it makes, I'll do them in green, is 60 degrees. So what I'm going to do now is calculate the vector F1. So we're going to do the vector F1. And I'm going to get its X component, and I'm going to get its Y component. And they want all these to be to decimal places. So I'm not going to do exact values, so I won't need to worry about my unit circle. The X component is going to be the magnitude of it times the cosine of its angle. The magnitude of it times the sine of its angle. So this is going to be 15. The cosine is 60 degrees. And this guy is going to be 15 times the sine is 60 degrees. So I'll go to the calculator and we'll do 15 times the cosine of 60 degrees. And the answer I get is 7.5. And then you go 15 times the sine is 60 degrees. And you get, what do they want? 2 decimal places. So you get 12.99. Let me check that. Huh? It was 12.99. Yeah. Technically, that's 13.00, right? Which is really kind of strange, and that's what got me. So I now know vector F1. It's 7.5. 13.00. And that's us done the first one. Now I'm going to do F2 and F3, and then all I need to do is to add the 3 vectors together, and we're good. Right? Now the second vector, you can make a mistake if you're not careful. It's this one over here. It's going to be called F2, and that's 12, and the angle is going to be 30 degrees. At least that angle that they give us is 30 degrees. So let's see what F2 looks like. Well, its X component is the magnitude of it times the cosine of the angle. And the Y component is the magnitude of the vector times the sine of it. In this case, the magnitude is 12 times the cosine of somebody, and 12 times the sine of somebody. And the mistake you're going to make, which is quite understandable, is you're going to think the angle is 30 degrees. We always measure angles from this x-axis, right? This one here. So the angle I really want is that angle, right? So how big is this angle? I'm going to short the colors here. How big is that one, which is the one we really need?
150.
You all comfortable about 150 degrees? So plug it in. Hit some buttons on your calculator, and that's that one done. So 12 times the cosine of 150 is negative 10.39. And 12 times the sine of 150 is 6. Yeah, I guess some numbers come out nice, some don't. And that's the second one done. Only one more to do and we're finished. So the third one looks like this guy here. And the angle they give me is 20 degrees. And they tell me that this is 9. Oh, better put the value in for F2. Negative 10.39 and a 6. And the last one then, F3. That's the next component. It's going to be a y component. The magnitude of the vector cosine theta, the magnitude of the vector sine theta. That's going to be 9 times the cosine of somebody and 9 times the sine of somebody. I'm not going to use 20 degrees. The angle theta is always measured from the positive x-axis, so I have to go all this way. So what angle will I be using in my calculation for this last one?
200 degrees.
Right? 180 plus 20 more. And then it's hit the buttons on your calculator. So 9 times a cosine ends up being negative 8.46. And 9 times the sine of 200 ends up being negative 3.08. And that is our last one. Negative 8.46, negative 3.08. Which gets us to the first of the two answers they want. Answer A wants us to do the resultant force, which is basically what you get when you add all three forces together. So that is going to be 7.513. The second one was negative 10.396. And the last one was negative 8.46, negative 3.08. And well, I'll add those three together to get the first one. So let's see what that looks like. 7.5, essentially take away 10.39, take away 8.46, and I get negative 11.35. And then we'll do these guys next. So it's going to be a 13, a 6, take away a 3.08, and I get 15.92. And very roughly, on my diagram, it would probably a vector going, you know, something like that, right? Just call it F. Would you agree that this vector is in the second quadrant? You agree? Second quadrant. That's going to be important for part B. Part B is, oh, take that away. They don't want to know that. They want to know another guy. They want to know the equilibrium. And the equilibrium force is dead easy. The equilibrium force is, what do you need to balance this one? Which basically means, what do you need to cancel them out? And it's the same two guys. With the opposite sign. If you added this to this, wouldn't they cancel out? Wouldn't you get 0? So that's an equilibrium force. It's whatever balances out the force that you've got. And you do that by making this positive and you make this negative. Now, the one that I thought they were going to do would be the angle that this vector makes. And that would be the inverse tan of y over x. So let's pretend they did part C. That's going to be 15.92 over negative 11.35. And the reason I wanted to do that question is because we need to know how to deal with this result. You're going to get a negative angle in a minute, I believe. And the answer you get is negative 54, let's say in nearest whole number, negative 54 degrees. That's not this guy. Isn't that angle actually in the fourth quadrant? If you draw negative 54 degrees, isn't it basically that angle? Can you see we want this one? So what is the correct direction for this resultant vector? It's not negative 4. How do we get the real one? What do you do to this number? That's another way of phrasing it.
At 180.
Yeah. And that's you finished. So we have done everything that you need to do for vectors. At least adding and subtracting and resultant forces. So we're now on to our last section. There is nothing else to do after this one. Get me, find the right number for it. It's section 9.2. And it's the dot product. So we're going to find how to calculate this thing called the dot product of two vectors. And then we're going to use it to, well, we'll wait until tomorrow to tell you how to use it. Right, suppose I have a vector u, and we'll call it u1 comma u2. And I have a second vector v, and we'll call this guy v1, v2. Then there is a calculation you can do on two vectors called u dot v. That's how you read it out loud, u dot v. It's actually the dot product of u and v. But most people just say u dot v because it's a lot easier than saying the dot product of u and v. Now, what is this calculation? Or at least, how do you do it? And you basically just do this. u1, v1, right? So u1 times v1 plus u2 times v2. And that is called the dot product. It's not the worst calculation in the world. Great. So let's just do some practice at calculating some dot products. So here's my first example. Suppose U is vector 1, 3, and V is the vector 7, -2. Then U dot V will be 1 times 7 plus 3 times -2. And what's that? 7 take away 6, and the answer's 1. Would you agree that's not the worst looking formula in the world to use, right? If you want to find the dot product of two vectors, multiply the x components together, multiply the y components together, and add them, and you'll get a number. And that number is called the dot product. How about this one? So U dot V will be 3 times -1 added to 2 times -3. That's -3, that's -6, and you get the answer, -9. So dot products could end up being positive answers, right? +1. Dot products can be negative numbers, right? And this is my third one, which is actually of the three the most interesting. If you do this dot product, you get 5 times 2 plus -2 times 5, which is 10, take away 10, you get 0. So a dot product can basically be any number in the universe, right? Can you get positive, negative, and zeros, right? All things are possible. But why is this one kind of more interesting? And it's for this reason. If the dot product is equal to 0, then the vectors U and V are perpendicular. What does perpendicular look like? The two vectors U and V will make a right angle. So U and V are perpendicular. U and V are at right angles. And U and V are orthogonal. Has anybody heard or seen the term orthogonal before? No. Orthogonal is the term that we like to use when two vectors are at right angles or perpendicular. These are all the same thing, they're just meanings. And the reason why we like the word orthogonal is not because it helps much in a 2D situation, it means exactly the same. But if you do vectors in 3 or 4 or more dimensions, you can't really talk about things being right angled or perpendicular because those concepts don't make sense in 4 dimensions, whereas orthogonal does. Now, if the dot product is a positive number, then the vectors U and V will be obtuse. In other words, the angle between them will be greater than 90 degrees. I don't know if that looks greater than 90, but it's meant to. And I just got that the wrong way around. They're acute, which means the angle is less than 90. And when it's negative, then I'll make it much more obvious. There we go. That's better. When the dot product is negative, then the angle between them is more than 90 degrees. So I can tell just by looking at the value of the dot product, whether the two vectors u and v are going to make an angle that's less than 90, that they're going to make an angle that is 90, or they're going to make an angle that's bigger than 90. And the rule is positive number, acute, negative number, big, obtuse, 0, right the Goldilocks spot, right in the middle. Are we good so far? You happy with a dot product, how to calculate it? And that it can simply tell you a little bit about the angle. So let's change some letters and then show you the next piece of the puzzle. Let's choose different letters. 1, 4. Now, if I found the dot product, A dot B, it's 1 times negative 2 plus 4 times 1, which is negative 2 plus 4, which is 2. What can I say about the angle between them, which we're going to call theta? Obtuse, acute, or 90?
Acute.
Acute. To remind you, acute means the angle's less than 90. Wouldn't it be better if we could get more detail than just it's less than 90? Wouldn't it be nice if there was a way to find the exact value between any two vectors, no matter how they're orientated, right? Wouldn't that be cool? And I didn't think we would get it today, but we are. So let me tell you the formula. Imagine I have a vector u, and I have another vector down here called v, and we call the angle between them theta. Then the dot product formula allows us to calculate the angle theta. And this is what the formula looks like. The cosine of angle theta. Oops, better get my letters right. U dot V divided by the magnitude of U times the magnitude of V. And that's the dot product formula. There's a couple of versions of it, but that's the one you use if you want to find the angle between any two vectors. So let's use the one that I just set up a moment ago, this one. Already found that guy. Let's find the magnitude of vector A. In this case, 1 squared plus 4 squared, which is the square root of 17. And the magnitude of B, which is negative 2 squared plus 1 squared, which is the square root of 5. So the cosine of theta is, in this case, the vectors are called A and B, so it's A dot B over the magnitude of A times the magnitude of B. And that gives us that the cosine of theta should be 2, that's a dot product, divided by this guy times that guy. Oops. How can I find angle theta if I know what cosine of theta is?
The inverse cosine.
Okay. And unless the question tells you, we will assume the answers are going to be in degrees. Now, I'm going to do this wrong. Maybe you can find out what's wrong. First, I'll tell you it's in degrees, so that's not what I'm going to do wrong. Come on, there we go. I'm going to go inverse cosine. I'm going to go 2 divided by the square root of 17 times the square root of 5. I'm going to hit enter. Two divided by the square root of 15 times 5, square root of 5. Looks perfectly correct.
Wouldn't you have to put parentheses
Yeah,
on
you
the
will.
17 and 5?
You do. So you have to go 2 divided by, I call them brackets, but parenthesis is American name for it, so that's fine. 17 times 5. And that's probably a different mistake. And the mistake is I forgot to clear the old one out. It was still using the old answer. So 2 divided by a bracket. Square root of 17. Close the bracket. Times square root of 5. Close that bracket. And I think I need one more. And there's the answer, 77.5 degrees. So what we have now is a method for finding the angle between any two vectors. What would happen if I did a question and the angle came out to be 0 degrees? What would the two vectors A and B, what would be the connection? How could you get an answer of 0 degrees from two vectors?
Would they be parallel?
They'd be parallel. Can you imagine that was U and this was V? You can't really do them one at a time, but wouldn't that be an angle of 0? What would happen if the answer I got was 180 degrees? What would that look like? How would the two vectors be orientated to make 180 degrees up? So there's my U.
Wouldn't they be opposite?
They would. Can you see 180? So no matter what the connection, right? No matter how the two vectors interact, this formula is going to figure it out, right? It's going to tell you, oh, they're 77 degrees. They're 125 degrees. They're 0 because they're parallel. They're 180 because they're pointing the other way. Technically, they're still parallel, but they're pointing the other way. And that is a perfect place for us to finish for today. So last name and bye-bye. Just to keep reminding you, Sunday is a drop dead date for all assignments.
I do
That's
have a
it.
question.
Mhm.
When you did the vector for A times B, which equals 2,
Yes.
how do we find out the degree was less than 90 or a cube?
Oh, when this number is positive, any positive number, right? 5, 7, 2, it's always going to be a cube. If this number is -5, -2, then it's going to be obtuse. And if it's 0, it's going to be 90 degrees. So if the dot product is a positive number, it's guaranteed that you're going to get an acute angle. All we're doing here
Okay.
is finding out what that angle happened to be. But I can tell you for sure it's going to be acute. And if it's
And
a
why
negative number, I can tell it's going to be obtuse.
is there
How
like
do
a
I know
reason
that?
for that, or
Yeah,
yeah?
if you plug a positive number in here, the bottom's always going to be positive. Isn't the cosine going to be positive if the top's positive? And a
Mhm.
cosine is positive in the first quadrant, acute. A cosine is negative in the second quadrant, obtuse. So when the dot product is negative, this will be negative. And if this is negative, theta will be in the second quadrant. So that's kind of the reasoning.
Okay.